So these were our derivatives. And basically those are three. Cosine and sine were pretty much the same except for the negative. Tangent and cotangent were the same except for a negative. Secant and cosecant were the same except for a negative. So when we get into integration, then we can really just consider that one formula. So we said that the derivative of arc sine is what? U prime over the square root of 1 minus u squared. So if we think in terms of u prime being du, if we need to integrate du over the square root of 1 minus u squared, or if we happen to have a negative in there, if I had a negative in there, all we'd have to do is pull that out front, and it would be the same formula. So whether we have a minus there or not, that's still basically going to integrate into arc sine but where in the derivative this was always 1, in the integration formula it turns out we could have different numbers there. So if that number varies, then we basically divide u by that plus c. If we need to integrate du over a squared plus u squared, which is kind of like u prime over 1 plus u squared, which that was the derivative of arctangent. It turns out this integral is 1 over a times arctangent u over a plus c. And one more, du over u times the square root of u squared minus a squared, 1 over a arc secant of the absolute value of u over a plus c. Now, a couple things that are important to note. A is a constant that's just going to be a number, where u is essentially a function. It contains a variable. So in this first one, we have the square root of a constant minus a function. On this bottom one, we have the square root of a function minus a constant. And that's important. We can't just factor out that's the same thing, because it's not. Because we can't take the square root of a negative, that's undefined. So that's going to help us a little bit in determining what a is and what u is. But always remember, a is your constant, u, so u is your variable. A is your constant, u is your variable. And the trick on all of these is going to be picking the correct thing to be u. Now some of them are fairly straightforward, but some of them are going to be a little bit more confusing. Let me show you a list. This is example 6 on page 379. And we have some functions that are very similar, but they integrate very differently. If we look at this one, you may notice there's a connection here. If we were to let that be u, that's just the derivative of that. If u was x squared minus 1, du is 2x dx. So if we put a 2 and a 1/2, we could just change that to 1/2 the integral of du over the square root of u, which we can change that to u to the 1/2, move that up, and use the power rule for that. This is very similar. The only difference is instead of having an x on top, we have an x on bottom, but this integrates completely different. If we look back at our formulas, we have one that has a square root of a function squared minus a constant squared with that function out front. So let's see, can we copy this? Yeah. Yes. So if we consider, notice we have a variable squared. How could we write 1 as something squared? That's just 1 squared. So our u, if u squared is x squared, then what's u? X. A squared is 1 squared, so what's a? 1. So what if u is x, what's du? Dx. So we basically have du over u square root of u squared minus a squared. We have that, which that integrates into one over a arc secant absolute value of u over a. So 1 over a arc secant absolute value of u over a plus c. Very different. This last one, we don't even know how to integrate that yet. We don't have a formula and we can't do a substitution yet that would give us any of our formulas that we know how to integrate. So just by changing things up just a little bit, by having an x here on bottom, or having an x here on top, or not having an x, it completely changes which formula we rewrite it into. The first one we rewrote into that. The second one we rewrote into that. The third one we don't even have something we can rewrite it into. It's not always going to be completely obvious what we need to pick. So sometimes we're just going to have to experiment a little bit. Let's try a few. Let's try this one. We'll look back to our formulas, our new formulas. Does it look like it could be one of those? Might be that middle one. Might be that middle one. So if it is, that would be our a squared. That would be our u squared. So if a squared is 1, what does that make a? 1. If u squared is 9x squared, what would that make u? 3x. The square root of that is 3. The square root of that is x. So what would that make du? 3 dx. Now this 12, that's just a constant, so we can pull that 12 out front. We can put that dx there. And if it fits the formula that we picked, what we need is du over a squared plus u squared. Well, we have a squared, we have u squared. To get du on top, what's missing? Or what else do we need? We need a 3. Well, if I put a 3 on top, what do I have to put on out front? Yeah, a 1/3 or say 3 on bottom. So what we have is 4 times the integral of du over a squared plus u squared, which integrates into 1 over a arctangent u over a and then plus c. Well, what was our a? Our a was 1, so 1 over 1, that's just going to be 1. Arctangent u was 3x. 3x over 1, that'll be 3x plus c. Now, page 378, they give us a list of the formulas that we've run across so far in integration. So when we start trying to integrate something, these are the things that we need to keep in the back of our mind. Now, when we have things that involve fractions, some things need to jump out. Is it something that we can simply rewrite using the power rule, doing a little bit of algebra? If we can't simply rewrite it using the power rule, then keep in mind that the natural log, that's the integral of du over u. So you might think, okay, if the denominator I pick to be u, do I have the derivative of that on top? The other items involving fractions are our new ones. So we're basically going to have to think about, well, what is our u? With the u we pick, can we make it look like one of these formulas? And there will be some cases where we can't. There are times where no matter what you try, there's not a formula that exists that you can integrate that function with. In Cal 1, we briefly mentioned that if we have a definite integral that involves something that we don't have a formula for, then we can use like Simpson's rule or the trapezoidal rule to approximate that definite integral if we can't integrate, if there's not an antiderivative for that function. Let's look at an example. In this is not going to happen a lot, but I want you to be aware that this could happen. And this is something you kind of use as a last resort. Now this kind of resembles du over the square root of u squared minus a squared. It kind of resembles u over the square root, and I have these backwards. This should be a squared, this is u squared. Or this, u square root of u squared minus a squared. And I have one more thing wrong, and I think everything else is right. That should be a minus. So let me clean up this mess that I've written. Now, which one of these can we weed out right off the bat? The first one or the second one? Why can you weed out the first one? Right. This is the variable part, so that would have to be the u squared. That's the constant, so that could be the a squared. Those are in the wrong order. So it's not going to be that one. Now Caleb said the bottom one, and most likely the reason he said that is because we don't have, if u squared is e to the 2x, what would u be? Now that would be the derivative, but if we're talking about u squared, we discussed the other day that if I have a power raised to a power, how do I combine those? Multiply. So if I have things multiplied, I could write that as a power to a power. So if u squared is that, then what would u be? E to the x. So let's look at this as dx square root of e to the x squared, so that's u squared minus 1 squared. U squared minus a squared. Well, this formula has a u out front. So let's think about this. What would du be? If u is e to the x, what's the derivative of e to the x? E to the x. So not only are we missing a u out here, an e to the x, but we're also missing one up here. But wait a minute. What's u over u? 1. Now, in all of the problems we've done before, we said that if we're missing a variable, we can't just put a variable here, put one over that. What we should have said, and I was kind of careful with this because I didn't want to confuse us too much, if we're off by a variable, we can't do that. We can't pull a variable out from our integration. We can pull a constant out front, we can't pull a variable. But there's nothing wrong with doing that. We didn't put that out front. E to the x over e to the x is just what? 1. If I multiply something by 1, does it change how much I have? No. So notice now that is du. This is u square root of u squared minus a squared, which integrates into 1 over a arc secant absolute value of u over a plus c. So 1 over 1 arc secant absolute value of u, plus c. E to the x, is that ever negative? If you take a positive number and raise it to a power, is that ever going to give you a negative number? No. So we can really drop the absolute values there. Because it's impossible for that quantity to be negative. So arc secant e to the x plus c. Now, granted, that's not going to happen a lot. That when we find du, that if we're off by a variable, we're just going to pick that variable up on top and bottom. But that is an option, as long as we don't put the reciprocal of the variable out front. Let's look at another. We look back to our list. Let's zoom in on these bottom ones. Do we have a constant squared minus a variable squared, or a variable squared minus a constant squared? Constant minus variable. So which of these that have a square root on bottom does it most look like, 18 or 20? 18. So du over the square root of a squared minus u squared. Now, a problem jumps out at me right off the bat. In this formula, there's not a variable in front of the square root, but there is here. Now, that might be taken care of. If it's going to fit this formula, what is our a squared going to be? Our a squared would be 1, which means that a would be 1. What is u squared? Right, that would be u squared. So what would that make u? Natural log of x. Well, if u is natural log of x, what is du? 1 over x dx. Notice if we move this around a little bit using commutative properties, we could do this. We could bring the x on the other side. Like that. Aren't those the same? We have a product of x and that square root on bottom. We have 1 on top, dx on the end. Notice doing that, all of that is du. So that's du. A square root of a squared minus u squared. So we could put that on top and call that du over the square root of a squared minus u squared. Du over the square root of a squared minus u squared. Which that integrates into, what was that, arc sine u over a plus c. What that is, yeah, arc sine u over a plus c. Where our u log of x, our a 1 plus c. So while right off the bat it looked like we had a problem because of that variable out in front of our square root, once we determined what a would have to be and u would have to be to fit our formula, then it turns out that we really didn't have a problem after all. That was all part of our du. Now, a lot of these work out nicely for us. A lot of them, we'll have an a squared and a minus a u squared, or for the ones that work out to be the tangent, we'll have an a squared plus a u squared. But the question is, well, what happens when we don't have something that fits that just quite right? We don't have just a variable squared and then a constant on bottom. Previously, we had a variable part raised to the second power, and then we had a constant. Here we have another term. So what we're going to have to do is we're going to have to do a little bit of algebra where we complete the square. We're going to take that x squared plus 4x with some number, and we want to find out what number would make that a perfect square trinomial. So if we have x squared plus 4x, x squared plus 4x, and let's bring the 13 over here. How do we find out what number, when added to that, would make it a perfect square, make this part a perfect square? Yeah. You could, but there's a shortcut. Remember, we take half of that coefficient and then square. 4 divided by 2 is 2. 2 squared is 4. That's a perfect square trinomial. Now, I can't just add 4 there. I could also subtract it. Now, a lot of the times in the past that we completed the square, we added 4 one place and then added 4 on another side of the equation. But there's not really an equation here, so I can't add 4 here and then add 4 on the other side. So adding 4 and subtracting 4, that's basically not changing how much we have. Those two essentially cancel. So notice that makes our denominator. What does that factor into? X plus 2, x plus 2. 2 times 2 is 4, 2x, and 2x is 4x. So that factors to x plus 2 squared. Then what does this make? 9. Does that look a little bit more like u squared plus a squared? Yeah. Now we have a variable part squared and then a constant part. And it doesn't have to be that that number is a perfect square. We could have, let's say, a 7 there. It could be that a squared is something like 7. That would just make a the square root of 7. But whatever is our u squared, the rest of that has to be a constant. So that would make u what? Right, if that's u squared, then u is x plus 2. du, the derivative of that is 1 dx. A squared is 9, so A is 3. So essentially we have du, dx is just du. We have u squared over a squared. Du over u squared plus a squared. Remember, with addition, it doesn't matter the order of subtraction does. But that integrates into 1 over a times arctangent u over a plus c. So 1 over 3 arctangent u over a plus c. Don't fall into the trap of trying to multiply those together, because this is inside our function. We're taking arctangent of this expression before we multiply that times 1/3, so you can't simply multiply those 3's together. Let's look at another one similar to this. We won't finish the whole problem, but let's just look at setting it up. Is there a constant on bottom? No. No constants on bottom. Well, if we did that, that still doesn't really get us at a u squared plus an a squared. Good thought, but it just doesn't quite work. So there are a couple different ways we can think about this. Let's do this. Let's factor a negative out so that our square is positive. And let's try to rewrite this as a perfect square trinomial. So if I've got x squared minus 4x and I want to make that a perfect square, the number that gets added to that is half of that, half of negative 4, not that, half of negative 4, and then you take that answer and square it. So half of negative 4, negative 2, squared is 4. Notice that that's a perfect square because that factors to x minus 2 times x minus 2. So what did we add here to make that a perfect square? 4. Change colors. Now, we added a 4 on the inside of that parenthesis, but what's outside that parenthesis? A negative 4. Now, we can think about this all in one step, or we can do this. If we add a 4, what else do we have to do? Subtract a 4. Now, we don't want that inside parentheses. So if I pull that out of parentheses, I have to apply that negative to it. Right. So minus a negative, that's going to make that a positive 4 when I pull it out front. Which that we said is x minus 2 squared. So that gives us an a squared minus a u squared. All right, that runs us out of time, so I'm going to give you a variety of these to work on for homework. And you may notice as we pick up more and more integration formulas, it becomes a little bit more tricky to determine what our u is, because we can have, as we saw earlier, 3 functions that look almost identical that are off by just one letter, and they integrate into with completely different formulas. So part of it is going to take practice and trying to pick up on patterns. Okay, when I see this, these are the things I need to try to fit it into. I'll try to fit it into one of those. If it works, good. If not, then I'll ditch that and I go to the next option. But a lot of it is going to be about narrowing it down. Okay, we got this large list of things that we can use to integrate with. Which ones right off the bat do I know I'm not going to use? So then we kind of narrow it down. So take a look at the ones I assigned for homework, and then next time I'll take questions about those.